Thank you. Coming on in. All right, thank you. A very, very warm welcome to all of you this lovely afternoon. My name is Rebecca Nugent, and I'm the head of Carnegie Mellon Statistics and Data Science. And on behalf of the department and our home Dietrich College of Humanities and Social Sciences, it is an honor and a pleasure to kick off the 2025 Degroot Memorial Lecture. In 2026, which is just a few weeks away, we turn 60. It's absolutely remarkable what this department has achieved and how much it has grown over the last 60 years, and we're just getting started. We'll be celebrating with our alumni and friends all throughout 2026, which includes this April's Carnival events. But what better way to begin this celebration than with our prestigious endowed Degroot Memorial Lecture honoring the founding department head, Maury Degroot. So to share with us some history and reminiscences about Maury, please join me in welcoming Rob Cass, the Maurice Falk University Professor of Statistics and Computational Neuroscience.
So, on the job market around the end of 1980, I wanted a place that was hospitable to Bayesian statistics. That eliminated almost every academic statistics department in the United States.
I can't hear you. I can't hear you.
You can't hear?
No, it's too far.
How about this?
No, it's much better, yeah.
Okay, then I'll just... Should I repeat that, Brent?
Thank you.
Bayesian statistics. Here, attention. I discussed my situation with Michael Perlman, who had left the University of Chicago to become the founding leader of a new department of statistics at the University of Washington in Seattle. Perlman was what we used to call a mathematical statistician, which is how I saw myself at that moment, and I had gotten to know him pretty well. He told me it was important to go somewhere that had a major figure in statistics. George Box in Wisconsin was one of the biggest names in the field, but Perlman added emphatically, Maury Degroot at Carnegie Mellon was also a major figure. So the point of that story is that Maury was highly respected by a pretty hardcore of people doing mathematical statistics. The thing that brought him the most fame in that world, I believe, was his work in sequential decision-making, especially a 1962 paper and his highly original 1970 text, Optimal Statistical Decisions, which, among other things, was translated into Russian and Polish, indicating its importance for the spread of mathematical statistics. Although at the time of my conversation with Michael Perlman, that depth of respect for Maury was news to me, I'd already been aware of him because I had gone a couple of times to a conference on Bayesian statistics that met twice a year and really kept the field moving in an otherwise mostly unfavorable and sometimes hostile environment. The meetings were run by the econometrician Arnold Zellner, but I called it the Maury and Seymour show because Maury and Seymour Geister would always sit near the front of whatever room we were in and offer a steady stream of jokes interspersed with insightful commentary. The jokes and commentary came mostly from Maury, who was quick-witted and had a visibly agile mind. His remarks were often critical, but generally good-natured. I became aware that many younger faculty at that meeting who were then establishing their reputations were looking for his approval. If Maury showed enthusiasm, it clearly meant a lot. Maury did research on a wide variety of problems and wrote a handful of papers with his early star student, Prem Goel, who's here today. Just asked me to turn up the volume here. He loved teaching, and he wrote one of the most widely used textbooks of that era for undergraduate probability and statistics, and because our Mark Shervish agreed to revise it, that book lives on, now in its 4th edition, as Degroot Shervish. Maury also paid attention to and supported collaborative statistical research. One thing that had an outsized impact was his becoming principal investigator of a large training grant for psychiatric statistics in conjunction with the University of Pittsburgh's Western Psychiatric Institute Clinic, which is one of the biggest psychiatric research institutions in the country. This led both Joel Greenhouse and Brian Junker to come here as trainees, and then they joined our faculty. Many others cycled through, and Joel eventually took over that training grant from Maury. In all, it ran for 18 years. When Maury came to Carnegie Mellon, he was interested in the overlap between statistics and economics through optimal decision-making, which was fortuitous. He struck up a close professional friendship and eventually collaboration with Dick Sayers. That turned out to be crucial. First, for the founding of our department in 1966, and then for its rise, because Sayers went from being an influential dean at the business school to president of the university, and he conspicuously directed resources our way, encouraging strategic growth based on very strong hires. As Maury worked with the next generation, or the next level cohort, Jay Cadane, John Mahosky, Bill Eddy, and Steve Feinberg, a pattern was established not only in hiring, but also in the value-based, cooperative way we approached research and education. The department's legacy is due to many people, but Maury's passion for research and education, the effort he put into advancing the profession, and the delight he took surrounding all of it remains with us. When Maury got deathly sick at the early age of 58, it was tough on everyone. Joel and I talked many times about our impending loss of this great figure. It felt like he had wisdom he hadn't yet imparted to us, and maybe we should hurry up and try to elicit it. I once made a stab at getting some pithy advice, but it didn't go very well. Then, one day, Joel came back from visiting Maury in the hospital. He said he had been able to get a good answer when he asked Maury for one thing he did in his work life that might also help Joel. Maury replied, "When you go to a seminar, think of your question before you fall asleep." That was Maury.
I'm Larry Wasserman, and it is my pleasure to be able to introduce our lecturer, who this year is Tchetgen from the University of Pennsylvania. Eric is university professor in the Wharton School at UPenn, also appointed in the biostatistics department. He's been there since 2018, I think, and before that was at Harvard. Now, I first heard about Eric when he was a student. A colleague of mine, Jamie Robbins, said, "Larry, you're not going to believe the student I have. This kid is just amazing." And every time I talk to Jamie, the first thing he said is, "Oh, you got to meet Eric. This guy is just unbelievable." I finally met him. I don't remember exactly where we first met. But yes, I got to know Eric's work and got to know Eric. And yes, he is amazing. And so we're very lucky to have this amazing person here today. Eric has done so many interesting things. He's extremely prolific. He's especially known for his work in semi-parametric inference and causal inference, higher order influence functions, and many other things. He's won many awards, and I'll just mention two of the most prestigious ones. In 2022, he was a co-winner of the Rousseau Award, which is this $1 million prize now referred to as the Nobel Prize of Statistics. And this year, he's the winner of the David Cox Medal, which is a joint prize from the Mendelian Society, the ASA, and the IMS. So let me just say a word about what Eric's going to talk about today. He's going to talk about something that he invented called proximal inference. So for those of you who know about causal inference, you know that the most difficult problem one always deals with in causal inference is the potential for unmeasured confounding. And proximal inference, as Eric will explain, is a way of dealing with that. When I first came across Eric's first paper on this, I think it was a biometrical paper, if I remember correctly, he had a way of being able to recover a causal effect even when there was unmeasured confounding. And my first reaction is, nope, that's not possible. Eric must be making a mistake somewhere. There was no mistake. I went through the paper carefully, and it's just amazing. It's just mind-boggling. And since then, Eric's produced many papers with various colleagues about different versions of this method, which I still find, no matter how many times I see it, very, very amazing. I consider it one of the biggest breakthroughs in causal inference in many years. So please join me in welcoming our Degroot lecturer, Eric Tchetgen.
Thank you so much for the introduction. I think you should give my talk. It's so clear. It's a real honor and a real pleasure to be here today. You have a mic. I can move around. And he did tell me, remember to turn your mic on. Okay, can you still hear me? Can you hear me? Okay. So it's a real pleasure to be here today. I'm really excited to share my work. It's been amazing. It's a huge honor to deliver this lecture, the Degroot Memorial Lecture. And thank you so much for that background on Professor Degroot. I wish I were alive when he was, growing up, I should say. So what I want to describe today is, my talk is going to have two parts to it. The first part is really meant to be for a general audience, and it's very intuitive, very conceptual. And then it's sort of a background introduction to proximal causal inference. And the second part will be a little more technical and some interesting things that we've been thinking about in terms of the robustness of some of these methods to certain forms of validations. And so my goal is basically you be able to understand the jargon I have in the title here, which is just a bunch of words, technical words tied together. And my goal is basically you will be able to understand what every single one of them means in the context of causal inference. And this is we have a very large group of researchers, but I want to highlight two people in particular who are co-authors on the second part of today's talk. Shushi, who is at Michigan, and our postdoc Young Hoon, who is a real gem and was able to teach us quite a few new things, despite having worked on this for close to 10 years. Causal inference can be summarized in this graph. You have a treatment, you're interested in the effect of that treatment on an outcome, and you worry that if you don't have a randomized trial, that there may be some background factors that are common causes of the treatment and the outcome, such that if you do not account for them, even in the absence of a causal effect, you might find an association between the two. One way of expressing this formally is that you're interested in the average, population average treatment effect, also known as ATE. And that would be the effect, the potential outcome for the entire population if they were all receiving the treatment by an intervention. Contrasted that with the potential outcome for the same population if, contrary to fact, they were subjected to a control, not take treatment, Y0. The key identification assumption is, in fact, that you've measured all common causes between the treatment and the outcome. And the idea here is that, of course, in the sample, not everyone takes treatment, not everyone takes control, and people who take treatment might be selecting on taking treatment based on how sick they are, for instance. And so that's a confounding, those are the confounding factors. Ideally, often people rely on this assumption that they've measured all the relevant common causes. There's no one-measure confounding assumption. And that's effectively assuming that within levels of the covariance you measure, that nature ran a randomized trial. And so that's a useful analogy that if I were to adjust for all the confounders, I can imagine that nature ran a randomized trial, and so within level of covariance, I have causality. But of course, that's wishful thinking. Nature did not run a randomized trial, and you may not have measured all the confounders. And it's not empirically verifiable, and it's often validated in practice. So this talk is about what do you do in that case. Before I say more about that, well, so for instance, I'll give you an example that came up recently in some of my research, which is vaccine studying. So initially we had randomized trial of COVID vaccination, right? Those were the initial Pfizer and Moderna back at the beginning of the pandemic. But ever since we haven't had a single randomized trial, we will not have any other randomized trial. The way to evaluate whether the new vaccine every year or booster is effective is using observational data. It's effective against a certain strain is using observational data. And we'll never have a randomized trial, as far as I know, of COVID for these vaccines. There are several reasons for that I can go into, but I won't. And so observational data, the point I'm trying to make here is that we cannot escape having to to use observational data. There are many settings where the exposure is harmful and you don't want to randomize people to it, or you'll go to prison. And then there are settings where there are just resource constraints or political constraints, and so randomized trial is not possible. All right, so measure confounding therefore becomes a central issue. And to make your analysis compelling, you have to convince people that you've dealt with measure confounding. And so that's the level of importance of this problem. And a lot of statisticians are very skeptical about causal inference, rightfully so, I would argue, based on observational data, in the sense that it's often difficult to provide credible evidence that you've adjusted for all confounders. So the framework we're going to discuss today are ways of probing your analysis, and ways of probing your analysis in ways that I think one can reason about in a fairly coherent manner. And to try to deal with, directly address the skepticism by essentially evaluating how credible your inferences are based on some things that you may reasonably assume to be true. All right, so I wanted to put this slide just to sort of demonstrate, to illustrate how important these types of analyses are. So this is the requirements for reporting that was part of the editorial policies for authors of the AMA. And this used to be a policy for journals like JAMA. They essentially banned all causal language. And so the sentence here is causal language, including use of terms such as effect and efficacy, should be used only for randomized clinical trials and nothing else. There's been a change in the last couple of years. They've actually modified that policy because they've come to the realization that, in fact, there are many situations where you can actually do some fairly compelling, credible causal inference based on observational data. And so that's really important to emphasize and to develop and to think about methods to make these type of analysis more and more robust to this sort of caution. Not that the caution should go away, but rather that we should try to directly address it and not assume it away. All right, so we're not the first people, obviously, to think about unmeasured confounding. There's a huge tradition on instrumental variable methods. Imbeds and Angrist and Card got a Nobel Prize in 2022. A big part of that was actually their work on instrumental variable methods and its impact on the field of econometrics and economics in general. And so there's some pretty influential work that comes about that exists in trying to create credible causal inference method without assuming away the potential presence of unmeasured confounding. Instrumental variable methods do have this requirement that you can find a valid instrument that is essentially a quasi-experiment. This can be difficult to find, particularly in healthcare databases, and economists are particularly adept in their application in coming up with stories. Very compelling stories about why weather would be an ID, for instance, or how far you live from the ocean would be an ID. And so in healthcare, it can be much more challenging to think carefully about valid IDs. And so we try to think about alternative ways that are more tailored. And that you see that I'm particularly interested in healthcare. That's most of my applied work is in the health sciences. And what we came to the realization is that actually in a lot of those applications, there is a hidden treasure known as the negative control variable. And these are variables that allow you to examine associations where causal link is not expected. And so if you find a surprising association, you know that association might be reflecting certain biases. That's what I mean by probing your analysis. It's trying to evaluate known nulls in your analysis and seeing whether or not you reject those known nulls. Now, not rejecting those known nulls doesn't mean you don't have a problem, obviously. But it's an incredibly powerful alarm system. And it's one that one can reason about. That's really important. For a given analysis, I can try to think about my source of bias, and I can think about negative controls to try to probe that source of bias. Okay, so that's the claim here, is that we can work with this. I want to say that negative controls have drawn quite a bit of public interest. The government is interested in them. the FDA started a program called the Prescription Drug User Fee Act. Back in 2023, they held a workshop on negative controls that drew a lot of interest. And then they had 2 grants that they put out, one Sentinel Tools on negative control automation, and one on double negative control adjustment. We got one of those to develop a framework to automate selection of negative control. And this is very important for post-approval surveillance studies where a drug is approved and then they have to continue to surveil for adverse events and detection and evaluation. And so we've been working through this with the FDA until 2027, where we're supposed to publish our findings and put out this tool for more broad general use. So there is a lot of interest. There's a need for more and more robust methods, automated methods, scalable methods. And so I'm going to describe first the line framework for this with a few examples, and then I'll jump into the method in the second half of my talk, if I can get there. So here's an example, by way of introduction, here's an example. We're interested in estimating the causal effect of maternal stress during pregnancy on the baby's birth weight. And so this is from a paper from Josh Davis Smith, where he had this really insight that, well, you can't really randomize, you wouldn't want to randomize maternal stress, or you would go to prison. And so what's a good probe as to whether or not that's confounded by environmental factors that you haven't accounted for? So the idea was to look at maternal stress, and arguably there would be no causal mechanism that would connect maternal stress with the baby birth weight, and there should be no association once you account for the correlation between paternal stress and maternal stress. And so you can see here that the expectation is that this causal pathway doesn't exist. Okay? No effect from father stress after adjusting for mother stress. And so a significant effect of father stress would, in fact, in principle, indicate hidden bias in your analysis. You haven't accounted for something, because this is a nonsense association. Okay? Family factors could be an unmeasured confounder, as I mentioned earlier, that you might worry about in these studies. And so paternal stress level is actually a really good negative control in the sense that not only does it not have a causal, you don't expect it to have a causal effect on the outcome, but you expect it to also be associated with family factors. So it needs to be relevant. And this is a really key element. It needs to be relevant for the source of confounding you worry about. So this is, going back to Larry's introduction, there is no magic here. This is a method to allow you to detect and potentially account for known but unmeasured sources of confounding. Okay? Not for unknown and unmeasured sources of confounding. So this is a method that's designed for the best observational studies you aim to conduct. One of the best observational studies you aim to conduct, the ones where you think carefully about the confounding. And you worry about your ability to measure confounding. Okay? And so it's very important. This relevance factor is a design consideration that's incredibly important. You have to understand the study you're working on. All right, so I should say that such a variable Z, in this case, maternal stress level during pregnancy, is what we will refer to as a negative control exposure. We sometimes use the term proxy or negative controls. Today I'm going to use negative controls because it has that, I think there's a tradition in NP where people think of it that way, but I essentially mean the same thing in terms of their definition. It's more or less the motivation for the variable. So formally, the variable Z is a negative control exposure if it satisfies 2 conditions. The first one is, which could be summarized as Z, which should be independent of Y, conditional on the treatment, A. But more importantly, if you had measured, contrary to fact, you had measured Q, you conditional it, then Z would be separated from Y, given A and U. Not a testable assumption. This makes this a causal inference problem. Causal inference problem will have an untestable assumption somewhere. This assumption is not testable without making a different assumption. Okay? So if you're looking for the sleight of hand, that's where it is. Okay? This is a really important assumption, but we actually do think that this is an assumption we can argue about in any given application. The key to the assumption here is whether or not this arrow is present. And so it does not cause the effect Y, that makes it an NC. And we further, I had to assume that it's associated with Y only through U. And so it needs to be relevant for the source of a measured income. So sometimes I'll refer to that as U relevance. So that's an NCE. I'm going to use another example to describe an NC, or negative control outcome. So consider the study by Jackson and colleagues, where they were interested in one of these analyses of the influenza vaccination during the course of an influenza outbreak or influenza season on influenza hospitalization. And they did an analysis where an observational study on flu vaccine effectiveness where they found a 20% reduction in the risk of influenza hospitalization. And given the source of the data, they were dubious about whether or not this was causal. Whether this meant that if you were someone who took the vaccine versus not taking the vaccine, that would result in on average in a 20% reduction in your risk for hospitalization. The main source of concern about confounding here, the source of confounding is really healthcare seeking behavior. People who are more cautious about their healthcare are more likely to get vaccinated every season, and also more cautious about exposure to influenza vaccination. They will wear a mask when they believe it would be appropriate to wear one according to, for whatever reason that may be associated with wearing a mask. And so these are a particular type of individual, and so the problem is healthcare seeking behavior is incredibly hard to measure accurately. Okay? And so the question is, in this analysis, do we adjust it for all the measured covariates, which is usually age and some social demographics, income level and whatnot? Is that sufficient to adjust for healthcare seeking behavior? So what did they do? They did this analysis where they looked at injury and trauma as reasons for hospitalization. These are presumably reasons for hospitalization that influenza vaccination should not protect you against. And so you imagine that this arrow will not be present. Okay? And they found that, in fact, influenza vaccinations seem to protect, to reduce the risk of injury and trauma hospitalization by 20%. This is a nonsense association. You have reasons to be worried about. Very useful tool, very simple analysis, very compelling negative control outcome. Why? Because it's a proxy for healthcare seeking behavior. People who go seek healthcare at a healthcare facility because they have an ingrown toenail. I had one of those and I did not seek help. I stayed home and I was very determined to deal with myself. Right? And so that could produce this form of selection bias. Okay. So this is a formal definition of an NCO. It's kind of a mirror image of the other one, which is that conditional on the underlying U, W and A would be independent. The NCO would be independent of treatment, conditional. There's no arrow between Y and W here, but there may be other common causes between the two, and that would be fine. Or they could get a direct arrow from W to Y, and that would also be fine. All right, and so we have two tools to work with. We have an NCE, a negative control exposure, and an NCO, a negative control outcome. And they form this graph, and in fact, you can add an arrow from Z to A or from A to Z, or you can add an arrow from W to Y, but not from Y to W in general. Negative control outcome is must satisfy W is independent of A and Z, of the primary treatment of interest, and negative control exposure when you bring them together, conditional on the unmeasured confound. And then NC is independent of the outcome, primary outcome of interest, conditional on U, and very important to further conditional U. Okay? If you don't want to think about the math, just think about the DAG. You have these two proxies of the unmeasured confound variable. and one that can be thought as an auxiliary treatment or exposure, and the other one that can be thought of as an auxiliary outcome or proxy of the measurement problem. Okay, so why would we consider using two sources of confounding? Because it turns out that, as I demonstrated in the example, to test for whether or not you have a mesh confounding, it will often be enough to have one proxy or one NC variable. But it turns out, under certain assumption, which I'm going to try to make a case for, you can actually debias your estimator and reduce the confounding bias by leveraging both negative controls. And I'm going to try to do this in very simple models, linear models, which might shock some people because I belong to the cult of non-parametric estimation. But I actually believe that to understand most of statistics, linear models often suffice. Because if it doesn't work in a linear model, it will not work in a linear non-parametric model, often the case. And for causal inference in particular, the structure of the bias is very clear to see with linear models. So you can do a lot, you can get a lot of mileage with linear models. Oh, so this is the last thing that I said, that you can have these arrows, and the assumptions will continue to hold. So what you need are these conditional dependencies. Okay, I'm going to skip this. It's just to say that there are many DAGs that satisfy, it's just to reinforce the last one, there are many DAGs that satisfy those two conditional dependencies. I'm only going to emphasize one of them, is the instrumental variable DAG. So this is the instrumental variable DAG. The instrumental variable is in this case, it's a randomized variable that affects the treatment, but has no effect on the outcome other than through the treatment. It is independent of you. What's a good example? You run a randomized trial at Z, okay, of taking kid with a team of COVID vaccination, and then you have non-compliance. Some people don't actually take the 2 doses, the initial 2 doses. That's non-compliance. And so compliance, taking the treatment as a sign, is A. And the idea is that if you design your study well, so that it's doubly blinded, the only effect randomization can have on the outcome will be through whether or not you took up the vaccination. That's a very nice idea. And that will allow you to, in situations where the intent to treat analysis actually could yield invalid inference, that can happen, to still be able to learn about a causal effect. Okay. So my point here is that Z actually is a valid negative control exposure, satisfying that exclusion restriction on the direct effect. So the only question is, why is it relevant? There's no arrow from U to Z. But we actually need it to be relevant, potentially conditional on A. And if you condition on A, if you know anything about DAGs, conditional A is a collider on the pathway from Z to A to U. That creates an association between Z and U. It becomes relevant. So selection bias. So one situation where selection bias saves the day. Usually you don't want selection bias. Collider stratification bias. And it's nice because then IVs, if you think of IVs in general, you can recycle them, you can repurpose them as negative control exposure. And I can come back to that a little later if people are interested, because there are certain assumptions with IV analysis that you need that you don't need in negative control variables. And so it's another way of thinking of IV analysis. You could also have an invalid IV, and it's invalid here because this assumption that mesh confounding is independent of Z is validated here. But this is exactly an ideal NC. So that's another way of recycling an IV that you think might not be perfect. Getting perfect. There are other settings here that I'm going to have to skip in the interest of time. So this is a little bit of a show-off slide, as my kids would say, just to say that we've been incredibly surprised by the level of interest that proximal methods have galvanized. And so I put together a little timeline to show the evolution. Granted, a lot of these papers are from our group. There are many more papers from other groups. So it started as a bias detection tool. Then we developed identification methods. and then it evolved over time, and then there's been many, many more interest in terms of using them for Bayesian analysis, using them for network analysis, where you worry about homophily, latent homophily, and you want to account for it, and proxies are a useful tool. And the way I would like to think about it is, you have an idea of an analysis you would like to conduct, ideally, an oracle analysis. But for some reason you're missing some of the variables you need are not just missing. Missing means that for some people you observe them and others you don't, but they are actually hidden. You never observe them. And if you can think of proxies of those variables, then these tools will become useful under certain conditions to recover identification. Okay, so let me turn it a little bit more to, I've made all these claims, let me try to now convince you that at least in certain settings, they make sense, they hold water. So I'm going to use linear models. So here's an example where I still have my DAG, and the world is linear. So this is kind of path analysis. The coefficients associating the variables on the graph here. And I have a linear model sort of encoding these associations. So the mean of y given a and u is just a linear in a and u. A is the treatment of interest, and u is the confounding factor. There's some condition on u here, beta a will have, in principle, will have a causal interpretation. And the average treatment effect is in fact at beta. Now, if you were to fit, you can't fit this regression because you don't observe u. The most you can do is fit a crude association, which means by linearity, which is why linear models are nice, means that you're regressing y on A, and there are two parts of A. There's one that's causal, and there's one that comes from the association between u and A. And that's what confounding bias is, because you can't tell them apart. You get the sum of the two, because you get one coefficient for A. Okay? So that's confounding bias. And we call this the bias y of A. And that's beta u times the regression of u over. Okay. So we're going to try to learn something about that bias and remove it. And that's where the negative control variables will come into play. So what we'll do is we will evoke a negative control outcome. And again, remember the world is linear. So I'm allowed to write a linear model for the mean of w given a and u. And because it's a valid negative control outcome, when I condition on u, it doesn't depend on a. And so what's nice about this model is that there is no treatment effect of A. And so it's pure bias. Which means that if I regress W on A, I get only bias term. Right? It looks like this term, and it's not a coincidence that it's linear in the bias, because I chose linear models for this reason. This is linear in U and E, the mean of U and E. This is linear in the mean of U and E. But the coefficients don't match. This regression doesn't allow me to use beta U. Just an aside, because I met with a number of people today, we had some interesting conversation about difference and differences. Difference and differences is exactly assuming that this coefficient is equal to that coefficient. And that W is your pretreatment outcome. So difference is a special case of this. That's one way of thinking of it. We're relaxing that parallel train assumption. However, we get this proportional bias assumption that the bias of W and A is proportional to the bias of YA. So we now have the negative control outcome that gives us this proportional bias, and we need some way of identifying the proportionality constant, and that's the rule of the negative control exposure. And so what we do is we repeat the same analysis now, and we regress not only on A, but also on Z. And so when you fit some condition on Z now, Z doesn't appear here because some condition on A, but Z appears here. So the bias YAZ now also depends on Z, because Z is relevant for you. It's associated with you. And so we recover, we'll do the same thing for W. Again, this proportional bias equation, and we recovered this equation. Now, you can immediately see why, hopefully, why Z helps. Because without Z, I can't tell these two apart, because they're both linear in A. They're both, A is binary. So they will be perfectly confounded. But suddenly, I have an effect of A that's associated only with Z. That creates exogenous variation to tease apart the selection bias due to confounding from the causal effect. So W captures the scale of confounding bias, and Z recovers, captures the confounding bias up to a scale, and Z recovers the scale. So what does that look like in practice? Literally, you run a two-stage regression. You regress W on A and Z. You get the fitted value for that. And you regress Y on A, and your fitted value for W, A, and Z. That's it. This factor will capture the latent unobserved U. And the coefficient beta A here will be the coefficient that you would have obtained had you measured U and adjusted U. So you can fit a two-stage regression. That's how you do it. If you're familiar with ID methods, it's like ID, two-stage regression. The only difference is the first stage, you're not regressing the treatment on the ID. You're regressing W. W is what's playing the role of the endogenous variable. And Z is playing a role of an ID for W. And A is just a covariate. So the nice thing about this is you can use ID software to run this analysis. You don't need to program anything new. And it'll provide you the value confidence interval accounting for that first stage regression. All right, so hopefully there's no magic here. Very important point I need to make. Note that the coefficient beta W is actually the ratio of these two coefficients, where eta U is how strongly correlated is your outcome proxy or your NCO with the measure confounding. That's that point that I was trying to make earlier that I mentioned, that you need something that's relevant. If that coefficient is 0, things are going to go up because you divide them by eta. That's the role of relevance. Okay? So it's like a form of specificity. You got to think about the source of confounding. Okay, I have about 15 minutes left, and I do want to leave some time for questions, so I'm going to skip a few things. I'm going to skip the non-financial identification part and get to the interesting part. The only thing I want to say is that we can now do this actually without assuming linear models. We can do this completely non-financial. And it involves solving for what we call a bridge function. And one way to think about the bridge function is playing the role of that linear model in W, in the second stage. Is we would assume that there exists a function of the treatment in W such that if I take a regressive function on A and U, I recover the mean of Y being A and U. And what we'll do is we'll take an empirical version of this, which integrates over U given Z, and we'll need to solve this integral equation, find H that satisfies this Morgan equation. We have conditions under which a solution exists for this integral equation. It's a very well-known form of integral equation. It's known as an integral equation, a Fredholm integral equation of the first kind. So there are sufficient conditions for the existence of a solution. That solution need not be unique. And we now have tools to estimate that function using your favorite machine learning tool and adversarial learning. And we have methods for inference. And the AT then takes that solution and just uses it as an outcome and runs the usual G formula on it. If you're familiar with the G formula, I apologize to introduce you jargon. But essentially, this in the standard setting where you're assuming no measure confounding, this would be the regression of Y on A and W. And so what this highlights is that when you have no measure confounding, it's really an inverse problem. Because U is latent, you need to learn something about something that's latent. That is an inverse problem. And so it's no surprise that you have to solve an inverse problem. These integral equations are inverse problems. Okay, that's all I'm going to say about that. And now I want to talk about, this is really nice. I described this, I'm going to try to do this in 5 minutes. I described this first part in a setting where you have ideal perfect proxies or negative control. I'm going to talk briefly about some recent work where we consider a case where you might think you have a negative control outcome that's valid, but you worry about a negative control exposure, and then we can also do it when both are invalid. Okay, I may just have enough time to describe the linear model version of it, so let me try to do that quickly. So imagine now that you're in a scenario where you have two candidate NCs, and I'm going to relax the assumption from assuming that I know that both are valid NCs to one where I'm willing to assume that one of them is valid, but I don't know which one. And then we'll scale it up. As in many applications, you may want to use many candidate NCs. And the idea here is you would run an analysis assuming a certain number of them are valid without knowing which one are valid. And you can vary that number and look at how stable your estimation process is. So the fact that Z2 affects YW here is that an oracle actually knows that this is not a valid NC, but you don't know it as an analyst. And you have a collection of two candidate NCs, and you want to recover an causal effect of A on Y, leveraging using these types of methods, without knowing which one is valid. Okay? So this is a form of robustness. If you've heard of double robustness is a version of this for estimation. This is a form of double robustness for identification. I have two causal models, one where Z1 is a valid negative control exposure, and one where Z2 is a negative control exposure. And I want to make inferences in the union of those models. And so we call that fortified as opposed to double robustness. That's one word, an additional word in that title, but you now understand what it's like. Okay, so Z2 is invalid because it directly impacts at least Y or W. And so class one is double NC will fail. And that is if you use the standard NC method, what ends up happening is you still get the bias structure here that's proportional, but then there's this residual term that corrupts your analysis, and you don't know which one it is. You don't know whether it's Z1 or Z2, and so you can't adjust for it. Okay. And so you no longer get this clean result that W captures the confounding bias and Z recovers the scale. W captures the confounding bias up to a residual term, where I'm using this notation where Z U star are all the possible invalid proxies with the number mu star. So in this case, mu star is just one, but you don't know which one it is. Okay, it just appears here. All right, so the idea of fortification is that at most, if I tell you a priori that I have P candidate proxies, and at most K of them out of those P are invalid, then any set of K plus one candidates must include at least one valid NC. So let me try this with two. I have two. Well, it's trivial with two, because I have two candidate proxies, and one of them is valid. Therefore, any set of two candidate proxies is a valid proxy. So the intuition here is that if you tell me you have 10 candidate proxies, and you tell me that at least half of them are valid, but you don't know which ones are. So 5 of them are valid, but you don't know which ones are valid. Then any function of 6 of the proxies must be a valid proxy. Because 5 of them may be invalid, but not 6. So one of them must be valid in that set. So any function of those 6 cannot cause the outcome. That's the intuition. So how do we translate this in practice? So here's an example. In my two examples, in the case where 2 is, I have 2 candidate proxies. And let's simplify things and say Z1 and Z2 are varying. Then I tell you at least one of them is valid, I don't know which one. So I know if Z1 is valid, then I could potentially use Z1 and the interaction between Z1 and Z2 as a valid proxy. Y and C. If Z2 is valid, I can either use Z2 or any function of Z1 and Z2 in the interaction between the two. So which one is always a valid proxy? The interaction. Because that's a function of both of them. And if either one is valid, that function of both of them cannot cause the outcome. That's the intuition. So Z1 and Z2 in this case, you can take an interaction. In general, you can take any non-trivial functions of all two of them. And now we can scale this up. So in the case where you have 3 candidates and you tell me at least 2 are valid, then I cannot use the main effects. I can't use the 2-way interaction, but I can use the 3-way interaction. Because at least one of these has to be valid, therefore the product cannot be invalid. And by invalid here, I mean causing either Y or the other. And so you can see where I'm going with this. We can essentially construct valid proxies for a pool of invalid proxies by generating these functions of, at most, if you tell me that you have P candidate proxies and at most K of them are invalid, then I can use interactions of non-trivial functions of K plus 1 through P interactions, or function of those components, as valid NCs, and the remaining ones, the lower order functions, need to be adjusted for. And I just simply rerun the 2-stage procedure, and that turns out to be a fortified analysis. There's a problem here, which is that if you go back to my binary example, you get all these interactions. So if main effects are hard to estimate, we know interactions are even harder. And so you may run into an issue of weak NCs. So that is a trade-off. You have to worry about weak NCs. And so we have methods to try to address that as well, which I won't have time to cover. So I'm going to skip ahead, because I think the only thing I wanted to say here this is a crazy slide, and I had to have it in there for Ed, is that you get this world. This is augmented IPW type estimator, and you get triple robustness like you would on a confounded. Sorry, I'm just talking to Ed now. and then, which is kind of remarkable that in this world where you have a measurement founding, it replicates a world where you don't have a measurement founding. I apologize for that. So simulations, I'll skip. The methods work when I simulate the data. Next thing is if you simulate the data, let's see if they work. And then I just want to have some time for discussion. So I'm going to skip the application as well and just go straight to my conclusion. But we now have these different universes. One where you're going to assume that your covariates are enough to adjust for confounding. And this is the standard methods for adjusting for confounding. You use the so-called G formula. You run a regression on the outcome of your covariates and treatment, and then you integrate over your covariates. And the value of the treatment you're interested in. That's the G formula. There's a lot of technology on that for doing that really well. And then we have now the standard proximal framework where you split your covariates into NCOs and NCs, and then you run the outcome confounding bridge or 2-stage D-squares, if you will. And now we have a framework that allows for some of the Z's to be invalid, and you have to tell me what your belief is on how many of them might be valid. And as I said, what we do is, I skipped this, but this is what we did in the application where we had 8 candidate proxies, and we repeat the analysis, and you could focus on maybe this one, where you allow 6 of them to be invalid, only 4 of them to be invalid, 2 of them to be invalid, none of them are invalid, and you look at your inferences, and you report all of those. Okay? In this case, I would argue that the results are sufficiently stable that you might say this is fairly compelling, that the methods are robust to invalid proxies. And to a measure confounding, they are fortified by simple causal inference. All right, so the last thing I want to say is that to allow for invalid negative control outcomes is actually quite simple under certain assumptions. You might work on the majority vote, which is a setting where you're willing to allow for at least at most 50% of your proxies to be invalid, the outcome proxies. In which case you can construct estimators that use one of them at a time, and you use a median of those estimators in that estimator rotating system. And we use subsampling for the inference in that case. And then we have some additional new methods now where we're interested in methods where you only have one kind of NC, E or NCO available, and you want to run these types of analyses that allow you to be robust to confounding and possible NC violation, NC assumption violation. All right, I'm going to stop here. Thank you so much for listening.
Yeah, we do have time for some questions. So are there any questions?
Can we do the mic up?
Oh, yeah.
Can you say hand?
Oh, there's hand, Mr. Rowe.
Appreciate it, thanks,
So, is this on? Oh, that.
Yeah.
So when I think about, more difficult situations, I was talking to my office about this, that I would come across. I always think about conditioning. And I sort of think Bayesianly without being Bayesian, meaning I think, okay, informally, what's the probability that these assumptions are, and then I just sort of say, okay, if these assumptions are true, then da, 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 da. And I kind of think, okay, yeah, they're pretty likely, whatever. And I come up with this conclusion is, reasonably likely or something like that. Very informally, because we don't have to come up. But now I'd like you to, and so we could do that with, if you go back to your negative control for exposure example at the very beginning, we can say, okay, father, stress, low probability that that's really going to have an effect, or whatever. And so, sure. But now I'd like you to put yourself in the shoes of the person who's actually deciding policy based on something that's in front of you, and someone's run this, I forgot what you call it, the very last, well, not just proximal, but the fortified.
Yeah.
So, and you've got a series of possible Ks, and now, on the face of it, it looks a little complicated to think about, because there's many possibilities there. But I'm just wondering, what would you, if you had to make a decision, whether to allow this or not allow this, whatever the situation, some treatment has got to get approved or something like that. What is it? What would you be focusing on?
Yeah, it's a really great question. Thank you for that. And I do want to say, we're all Bayesian at heart. That's the right way to think about it. Is I have a prior, and I'm putting a prior on how many prior boxes are. And you could completely do a Bayesian analysis of this, formal, and then do a decision analysis where you output a decision. I didn't do that, obviously. So the way I would think about it is, we plot this table. The policymaker will typically have one point estimate, confidence interval, credible interval, and that's it, they make the decision. I give you 4 point estimates that are increasingly robust, and they all are coherent. They all agree. To me, that increases the credibility of the findings.
I got that part.
So, in this case, the application actually showed that the treatment effect was harmful. Okay? And in this particular analysis, the next analysis that we did was, well, this is a population average treatment effect. Are they people who benefit from the treatment effect? That's the right next question. I would never say, because of this analysis, the treatment is bad, because it's an observational study. And because it's an observational study, you're not held bound to just give one population average treatment effect. You need to explore your data. The data is so much richer in terms of decision making on who takes a treatment and who doesn't. But you should search for individuals who might benefit and individuals who might be harmed. So I'm moving away from the policymaker and closer to the clinician who needs to make these decisions on a day-by-day basis. If there were no effect, it would be a very different conclusion. But if there is an effect, and it's harmful in this case, then you can get a more nuanced answer. I don't know if that answers your question. Probably not.
Not quite.
Rob, can you use the mic?
I'm not sure that's worth going into this anymore, but I guess what I'm struggling with is only, I mean, this is convincing right here. These, like, based on what you said, I think I've kind of followed it. It seems like, yeah, okay, it's robust. But so maybe you have to imagine a slightly different circumstance, and I don't have your experience to know what are the different circumstances. But I'm really asking: is there something that that you would be directing if somebody else does something and presents you with this? Is there something that you would push back on? Or not push back on, but would you kind of focus on? You'd say, well, what about this? What about this? What are the things that are kind of the key places where you would say, well, they might have made an unjustified assumption here?
I would start with ID. Nothing is ID. I mean, these are all models. So let me just explain my perspective. So I sit on advisory committees at the FT, where you get, whether it's trial or observational studies, and you have to make a recommendation.
Right.
And you poke holes in analysis. If it's an observational study or an imperfect randomized trial where you have the violations of protocol, the question is always confounding. So this is trying to address what comes up in those conversations. Can we poke at the confounding? Don't tell me that you've adjusted for everything on the sun, because you haven't. So can you make another assumption that might be reasonable? Well, I don't believe these effects should be there. And if you find them, I will know there's a problem in your analysis. You don't find them, I'm a little bit more comfortable, but not completely. We should never be completely comfortable. And so this is about increasing the credibility of observational analysis. It's never going to be foolproof. And I try to make it very clear that this is not going to say, oh yeah, definitely do this and don't do that. Because as you said, there are many factors. Measurement error, how selected were these patients. So I'm only narrow focused on one particular source of confounding, which usually is a debate. Look, I mean, like our air pollution policy, right? The EPA regulates how much air pollution, PM 2.5 you can have in the air, or it regulates industry for that. Every year they convene a group that discuss about it. And I can tell you that industry, their argument is, well, you didn't run a randomized trial. How do I know that the air pollution is bad for you? And epidemiologists are like, well, we try to address conventional confounding because that's what you think is a big problem. So this debate is not going to be resolved by any of these analyses, but we can try to make it a little more fortified.
Well, I was just going to ask, do we have time? Okay, I guess we do have time for another question or two. Then Rebecca, then we're not done. Rebecca has one or two things to say. So is there another question? I mean, I have a million questions, but I'm going to save them for Ed.
I'd really like to ask you about multiple robustness and stuff, but I was wondering if you could just tell us something about the story of how you developed this new framework, and for people that are aspiring to do this kind of work, what's the story behind it?
It's a wonderful story because it's not a story about me at all. Thank you for asking that. I should have started with that. So, sorry, I'm going to go back to the beginning. Okay. So in 2016, Wang Miao, who was a PhD student at Peking University in China, came to visit me as a visiting student in Boston. And he suddenly became obsessed with negative controls. We were supposed to work on missing data. I was actually quite upset. Because missing data problem, and he would come back to negative control. And our first paper, biological paper, 2018, was basically his work product. He had this insight, and I worked on his English. Right? But he had this insight that he took 2 papers of ours that we published, and then he realized that he could make it more functional. So that's the answer. Wang Miao came up with this process. We've collaborated over the years, and we've been able to develop it. And so this is really a group effort. It's not my creation at all. We all contribute to it. So thanks for asking. So, good students and good postdocs. And as far as I can tell, you got plenty here.
Yes, we're lucky we do have lots of them there. So maybe one more question?
Can you go back to the example you talked about the father's stress, mother's stress, and the birthday? The first you have one. How would you?
Grandma, did we
How
give you
would
this?
Sorry. So in this example, how would you decide your analysis will solve this problem?
Could you say that again?
The analysis you did, you just talked about all the details. How will you solve this problem?
How would you decide?
Yeah, and how would you solve this problem whether or not father's stress, mother's stress, and the four variables you have? Ultimately, what is your conclusion about what the possible biases might be here?
So this was George David Smith example I should mention, and to give proper credit. The point he was making is there was this debate about analysis looking at the association between maternal stress and baby birth weight. And this was all based on observational data. And so he thought of this design, the study design, as one to probe these analyses for bias. And the logic here was that, well, the mechanism by which maternal stress affects baby birth weight during pregnancy, right, would completely block any association between paternal stress and baby birth weight, if or only if there were no unmeasured confounding. So this arrow did not exist. And so he used paternal stress as a way to look at for bias. And he found bias in some analysis, but not other analyses. Mm-hmm. And so that call in question didn't completely resolve the debate, but at least justified people's pessimistic view of some of those results, or critical view of those results.
So that's the assumption you're making, father's stress does not affect baby's birthday, right?
Yeah, so this is biologically based. There is no biological pathway.
That assumption is valid.
It is a valid assumption. There is, I don't know, is there an obstetrician in the room? There is no causal pathway between how stressed the father is.
How do we know that?
Sorry?
How do we know that? There's no causal
We talked to our obstetrician at Penn, and they agreed with it. There is none. Because the mother is carrying the baby. I know we like to take credit for a lot of things. There is no way to get through the baby other than through your stress affecting your mother's stress.
Yeah, father's stress could really affect mother's stress too, right?
Could you say that again?
Father's stress could affect mother's stress too.
That's right. That's why the arrow goes both ways. Doesn't matter. The point is that this arrow doesn't exist, so if you find an association between Z and Y, it has to be because of confounding. It cannot be causal. That's the insight of his analysis.
So I have a hypothetical scenario with the father is
Jake, can you use the microphone, please?
I can speak very well.
No, it's for the recording. Thank you.
So just to add to this question, like why father stress doesn't have a causal effect. What if the father is stressful and he cooks not as well as he used to, or he smokes a lot? It can also contribute to the baby's weight.
That's about smoking.
Well, it's a consequence of stress.
That's about smoking. And the smoking is a you. Smoking is related to the father's stress, and smoking is related to the baby's birth weight. That's a you. You're making an argument. Thank you. That's what to worry about. This is meant to protect that.
Well, then the direction of the arrow is going to be from B to B.
Yeah, that would be fine if it's phase 2.
Okay, it is fascinating, but it's getting late, and we have more to do, so let's thank Eric.
All right, thank you very much. I myself have had 2 Well, thank you so much, Eric. So thank you so much for a wonderful talk and helping us honor our past and get excited about the future ahead. And as part of being the Degroot Memorial Lecture deliverer, we are pleased to present Eric with a plaque. Thank you. Well, of course, and it wouldn't be our department if there weren't swag. So Eric is now an honorary part of our family, our department family. So he gets the coveted Stat DS fleece. And I know the new students are like, where's our fleece? And it's coming. It's coming. All right. As well as the coveted statistics department hat. So getting ready for the winter. So thank you again, Eric. All right, so one more thing. One of the best parts of my role is the opportunity to connect with alumni and help connect them to undergraduate and graduate students. Their experience, advice, and generosity has been invaluable to our community, and we are very fortunate to have a growing network of alumni who are dedicated to this department and to Carnegie Mellon. So Rob mentioned it earlier in his remarks, but it's a great pleasure to have with us today Dr. Prem Goel, Maury Degroot's first PhD student to start in the newly formed Department of Statistics. So Dr. Goel has had an illustrious career, including faculty positions at Purdue University and Ohio State University, and serving as chair of Ohio State Statistics in the late 80s and early 90s. So during that time, he oversaw the development and delivery of a brand new data analysis initiative that ended up serving for the School of the Arts and Sciences, which ended up serving over 8,000 students every single year. So Dr. Goel was very much ahead of the data science curve. So Prem, it's been wonderful having you here and getting to know you. And my only concern right now is that you've been wearing Ohio State swag all day. So we're going to do something about that too. All right, so can we please pass this up? So Prem, yes, so Larry, you can take that up. So please join me in thanking Prem for giving him department. So again, thank you so much for joining us for the 2025 Degroot Memorial Lecture. Just as a reminder, we are turning 60 in just a few weeks, and we'll be continuing to celebrate and looking back at our 60 years of history and thinking about what our next 60 years looks like all this next year. So please make sure you join us at all of our events. Thank you so much.